Okay, so today I'll be presenting about using a package called priorsense for prior and likelihood sensitivity analysis. And this is based on work I've been doing with my colleagues Topi Paananen, Paul Björkner, and Aki Vehtari at Aalto University in the Cluster of Excellence SimTech in Stuttgart. General overview of the talk. I'll start with some motivation, why this prior sensitivity stuff is important, what this package that we developed is, before going through some two examples and some technical details of what's going on in the background at the end. And finally, some closing remarks. So for our motivation, well, choosing priors can be hard and time consuming. There are some really interesting tools for prior elicitation, but it's still an expensive process. So many people use shortcuts, default or template priors to just start with, see how well the model is going to work in that case. Lots of packages provide these kind of weakly informative default priors, but it's important that we should always check the influence of the prior, particularly in relation to the likelihood on the posterior. So we believe that semi-automated checks would improve the current, possibly ad hoc workflow for sensitivity analysis in this respect. So we developed a package called priorsense. So it's an R package with tools for semi-automated prior and likelihood sensitivity checks. It checks the sensitivity of these two components, or the posterior sensitivity, based on power scaling, which is essentially raising either the prior or the likelihood to some coefficient alpha and seeing how the posterior would vary. So this can be considered varying the strength of the prior or the likelihood. The package provides visual checks and a numerical diagnostic, which we'll see in a bit. And the current implementation works with stan, rstan, command stan R, and BRMS models, but the implementation is not tied to anything specific. The background can be adapted to further modeling interfaces. So the idea with priorsense is it gives a prior sensitivity and a likelihood sensitivity. And depending on the interaction between these two, we can diagnose what is happening in the model. We don't really consider the case when there's no sensitivity at all, so changing the likelihood of the prior doesn't have any effect on the posterior, because this probably indicates a pathological model where you have issues with model fit in the first place. So we can start by looking at what happens when there is no prior sensitivity, but there is likelihood sensitivity. So this in the bottom left-hand corner is what we would consider likelihood domination. The data is informing the posterior, the prior is having very little effect. And this is usually what our target is when we're using weakly informative default priors. We're not encoding specific information into our prior, so we want our likelihood to dominate. Alternatively, it might be the case that there is prior sensitivity. So we can have two cases there. When there is no likelihood sensitivity, we can have a situation where the prior is dominating possibly a weak likelihood, so in the top right corner. And this can come about when the parameters are not informed by the data. So increasing the strength of the data by the likelihood doesn't change the posterior for those parameters. Alternatively, when we have both prior and likelihood sensitivity, this is an indication of a conflict between the prior and the likelihood, prior and the data. And it's often the case that it's something we want to address, particularly when using default priors. So I'm going to jump straight into some workflow examples of how to use this priorsense package and how it works in practice. The examples will use BRMS with Bayes plot for some plotting and priorsense for the diagnostics. BRMS, if you're not familiar with, is developed by Paul Björkner, available on GitHub, and Bayes plot is developed by the STAN community, also available on GitHub. So let's suppose we take simple data, which is included in the base R, which is the plant growth data set. We try to model the growth of plants depending on whether they're given a nutrition enriching treatment or a control condition. We have 20 observations, 10 in each group. Quite a simple setup, and everybody loves linear regression, so let's just try a linear regression. In our BRMS, we would have something like this. It's a basic formula syntax with an intercept and then the effect of the group. In more formal notation, we can write it like this with the normal Gaussian and some priors. So BRMS by default will give some fairly good default priors for sigma and the beta intercept, but for the effect of the beta coefficients for the treatment, it defaults to an improper prior. So we're going to try to change that and actually use a proper prior. But what should we use? Well, let's just try something. This is unfortunately often the case that you're stuck with. You don't have much background knowledge. You've been giving this data. Okay, I need to fit a model. What are we going to do? Let's just try a normal 0 to 2.5. Maybe we could have a look at the prior predictive check, just see how well our prior is kind of approximating the data. So here we have different realizations from our prediction, prior predictive compared to the real data in the vertical line. And we can compare different quantities of the generated data. So the minimum value of the data, or the median, or the maximum. And based on these preliminary checks, the prior doesn't seem completely unreasonable. Yeah, maybe it's giving some negative values for weight, but that's probably an issue with the model and not the prior. So we go ahead and fit the model. We end up with a posterior for our treatment effect. And this is the effect of the nutrition, added nutrition on the soil. Based on the posterior, you might conclude, oh, it's possibly having a negative effect, if anything, but likely maybe no effect. But how sensitive is this posterior to the choice of our prior? Okay, remember it was just an arbitrary 0 to 2.5. This is where we can use priorsense. So this is a diagnostic plot that is one of the defaults from priorsense, in which we look at both changing the prior on the top, the power scaling the prior, and bottom, the likelihood. So we're plotting each different posterior that would be realized by changing the strength of the component based on its alpha value. So the higher the alpha, the stronger that component, prior the likelihood, and the lower the alpha, the weaker. In the top, we see that there's only one line, that everything's on top of each other, which indicates that changing the prior based on this alpha doesn't seem to do much to the posterior. Whereas on the bottom, changing the strength of the likelihood is narrowing the distribution when the likelihood becomes stronger and widening it when the likelihood is weaker. So this would be an indication that there is no prior sensitivity, but there is likelihood sensitivity. We could look a bit further in detail and look at some specific quantities of interest in the posterior. On the left-hand side, we look at a divergence metric from the posterior, the base posterior, compared to when we weaken or strengthen the two components. So the prior line in the dark purple is almost horizontal. There's not much difference when we are strengthening or weakening it, whereas the likelihood has a clear V shape. It's increasing in distance from the posterior, no matter whether we weaken or strengthen. We could also look at the posterior mean and standard deviation. And what we see here is, for example, the mean is having very little change, no matter whether it's the likelihood or the prior that's being changed. The dashed line indicates plus or minus 2 Monte Carlo standard errors. So anything within that range should be considered to be negligibly different. But the third plot is where we can clearly see that strengthening the likelihood is decreasing the standard deviation of the posterior. So the data is informing the posterior, as we would hope in a case of likelihood domination. Prior doesn't seem to be doing much at all. So with this in mind, maybe we can continue our analysis. But in priorsense, we also just have all of this in a single numerical value, which everyone seems to like, with cutoffs that you can try to look at quickly. So here we suggest a cutoff of 0.05 of this diagnostic, which is based on this divergence metric in the rate of change. As you see, the prior for all three parameters is not having much influence, whereas the likelihood is. Looking good so far. So we would maybe continue our analysis, maybe fix up the model a bit more, so we're not getting negative values, etc. So we can move on to another slightly similar, but maybe a bit different example, also looking at crop yield. But this is the NPK experiment, where we are looking at the effects of nitrogen, phosphate, and potassium on pea crop yield. We have 24 observations with all different combinations of this NPK applied to the soil. Again, let's try linear regression. Simple, it's easy. This is where people often start with. And we would end up with something like this. There should also be the Gaussian smoothing. But the key is we end up with quite a few parameters that we need to specify priors for. Again, BRMS has these default weakly informative priors for sigma and the intercept term. So we're going to try to choose a weakly informative prior for the beta coefficients. What should we do? Well, maybe we can just try the same prior. It seems to be a similar problem. Let's just see what happens. Prior predictive checks, the minimum. Okay, we're overshooting the minimum quite a bit. Medians looking okay. And maybe we're overshooting the maximum as well. But this is maybe a conservative, quite wide prior. It doesn't look to be too outrageous. So we go ahead and fit the model. Now, these are all our different parameters. We have the effect of nitrogen, phosphate, potassium, then the interactions. And it looks, maybe there is some indication that nitrogen has an effect. The others seem like maybe a zero, they all cross the zero, so it's hard to conclude much. But how sensitive are these to the choice of prior? Well, if we run it through the prior sense, we see quite a few diagnostic warnings. Prior sensitivity in all of these parameters, likelihood sensitivity in some of them even have no likelihood sensitivity, which can be a case of weak likelihood, but it could also just be that the prior is so strong, it's dominating. We can look at our diagnostic plots. So here we have two parameters, the effect of nitrogen and then the three-way interaction. We see above, again, what happens when we change the prior slightly and the likelihood below. As we can see, there's clear prior sensitivity and likelihood sensitivity for the effect of nitrogen, and it's kind of an opposite directional effect. In the interaction term, there's very little likelihood sensitivity, but there's clear prior sensitivity. So that could be an issue as well. We go ahead and look at just the nitrogen effect in detail. We can see what it looks like when there is conflict. So both have an effect on the divergence metric, and then we have this characteristic X shape for the mean. The mean is being shifted in one direction by the prior strengthening it, and the other direction when the likelihood is strengthened. And they're both affecting the standard deviation just because it's stretching out. So maybe the prior was completely crazy. So here is probably where we should readjust the model and think carefully about the priors. What should we do for all of these? Maybe we should do some prior elicitation, consult some experts. In some cases, because we didn't think too much about why we chose that prior, it's just arbitrary numbers, maybe we can just try a weaker prior. So let's just scale it by quite more than a factor of 10 and refit the model. Looks quite different now. The nitrogen effect is clearly positive and actually quite a higher magnitude. And some of the other effects have changed sign or at least shifted away from zero to some extent. We run through our prior sense diagnostics. There's no more prior sensitivity. So this concluded that maybe now the prior is weak enough that it's not informing the data. It's the posterior. It's not in conflict with the data any longer. And the likelihood is still informative. So what's going on in the background, the technical details of this? As I mentioned, we're using this power scaling transformation, but the key here is we're not refitting the model each time. we're using importance sampling to estimate these new posteriors. So we have this base posterior. We've got, for example, if you have MCMC Monte Carlo draws from it, and then we're going to use those draws by reweighting them based on the power scaling transformation. So we can derive these importance weights from the prior or likelihood evaluations themselves. There's no difficulty calculating them. And then we can use Pareto smooth importance sampling and importance weighted moment matching, which are techniques to improve the estimates. So importance sampling can often fail to shift the distribution too far, but these methods can improve and self-diagnose when our estimates are good and when they are not. Bit of details about the package, the functions itself. So what I've been using here is 3 of the functions, essentially. The power scale sensitivity will just give a table of these sensitivity values. Maybe it's the first thing you want to do. Maybe whenever you fit a model, just run that. Then you can look at creating a sequence of these power scaling posteriors to plot with the density, CDF, or quantities. In order to use these methods, you need to have the prior and likelihood evaluations for each of the draws saved. So in Stan, we can use the generated quantities block just to save, for example, the log prior. So the global log prior for each of the parameters. You could split this up into an array and have each prior separately. And then you can do a bit more targeted analysis of changing just a single prior. But this is the easiest way. You can do the same thing for the log likelihood. Often you might be using the log likelihood anyway for leave one out cross-validation if you're using the LU package. So some closing remarks. What priorsense enables, well, our goal is to enable semi-automated prior sensitivity checks in R. We have a Python version coming soon to the RVs package. And it's important to recognize that sensitivity is not always a problem. Here, I skipped over a bit of really thinking about why we have a sensitivity, because we just used an arbitrary prior. It's more of a tutorial on the package itself. But if you've elicited the prior and it is in conflict with the data, that doesn't mean that the prior is wrong. You should be really careful in changing your prior arbitrarily just because there is sensitivity. For further details, you can see the full paper, which goes into a bit more detail of the underlying principles on arXiv. We have our package also available on GitHub.